All right, so section 4.5 is called the fundamental theorem of calculus. And whenever mathematicians put the word fundamental on something, it means it's used a lot sometimes. Sometimes it actually means that it's very basic, like we use it all the time, kind of like what you're saying. You know, it's just so basic, it's just almost common knowledge. But all of the time what it means is it's really, really important, okay? So the first thing I want us to do is I want us to talk about, there's two parts to this theorem. We're talking about the part one. The fundamental theorem of calculus part one says the following. If we have a function that's continuous, it's a small f of x, and then its antiderivative is the capital F of x. So that's, you know, the basic skills quiz things you've been doing. That's the section 4.1 in your book, all right? The antiderivative is of capital F of little f. Then if we were to take the antiderivative, the definite integral is what this is called, from a to b of f of x dx. You saw that notation last time, maybe even 2 sections ago, actually, where we first saw it in 4.3. This can be found exactly, that is not approximating with rectangles, but it can be found exactly by taking the antiderivative capital F of x, right? Do you see this notation here? Same notation, and evaluating it at the point B, and then subtracting the evaluation of it at the point A. Okay? So let me kind of just give you a real quick and easy one so we can see this happen. So if this says it wants the definite integral, that means the area under the curve from 0 to 4 of 3x minus 1 dx. What this means you're going to do is you're going to first take the general antiderivative, the same way that you did before, okay? So let's take 3x minus 1. Actually, let's make it an easier problem to work with just so I don't have to deal with, well, 3's fine. We'll leave 3. No, I'm not. I was going to do a different one. But I guess it's very close to my first example, isn't it? I guess we might as well do the first one. Let me just write down the steps I was going to do, and then we'll do them on the actual example. So the first thing we're going to do is we're going to find f of x, the capital F of x, like the antiderivative, and then we evaluate. Okay, so yes, it's very similar to the first one. We might as well do the first one to show it. Excuse me. All right, so we're taking a look at this. This says basically that I want the area under the curve from 2 to 5, right? And it's the area of a specific type of function. This is a line. And the way we're going to do it now is we're going to do it with integration. Instead, like this one we could have done geometrically. We could actually draw this one. It would be really nice. It would be easy to work with. We're going to do it with this new process, doing it with antiderivatives. What's the antiderivative of negative 3x? Good. Negative 3x squared over 2. And then what's the antiderivative of 4? 4x. And then in your section 4.1, we did a plus c here at the end. I'm going to show you this for now, but my goal in showing it to you on this very first example is to show you that that plus c is not needed when we're evaluating it at the points 5 and 2. Okay? So I'm going to show you that part of it as we go. But for now, let's put the plus c. That's what we've been doing in section 4.1. And we're supposed to evaluate this at the points 5 and 2. So we write this sort of as a vertical bar at the end. The first number, the higher number on top, and then the lower number is the number from that was originally on bottom. So what you're going to show is you're going to show this number plugged in place of x. And I'm going to put this inside of brackets just to recognize that that's plugging in the number 5. And then I'm going to subtract, same thing, but with the number 2 plugged in. And the first thing I want to talk about is why in the world I said that the c wasn't needed. Can you tell now why? They're going to cancel each other out. I have a plus c here and a plus c here, but this plus c here has a negative in front of it. So these always cancel each other out when we do definite integrals. Definite integrals are the ones with the numbers on top and bottom, right? So there is no need to put a plus c on a problem if we were dealing with the area under the curve. That is a definite integral. Now I want to show you a couple things. Who has calculators with them today, like the TI 84, 83 types? Do people have those with them? Okay, you don't have yours. It's okay. Everybody else have one? Okay. Micaiah, look on with Grace so that you can see what I'm about to show you. I want to show you first how to do this particular problem, and then I want to show you a way that your calculator allows you to check all of this particular problem, okay? Because it's kind of cool. All right, so taking a look at this one first, you could take the number or the expression that we found right here and put that into y1 in your calculator, right? Do that for me real quick. Put that into y1 in your calculator. And then you can evaluate that at 5 and 2 using your table, right? We've been doing that now since maybe the first week of class, maybe the second week, I don't know. Something like that. So you can put in the part in red in your y1, and then you can just go into your table and put in 5 and tell me what you get when you do that, and then we can put in 2 and we'll tell me what that when we get with that. Did you get the number 5?
You get 12.5, and for 2 you get 5.
And do you get negatives or positives, or
They're both positive.
are they both positive? I thought that I remembered somebody told me last class that they were negative. I'm getting a negative on mine.
Wait. I did it squared.
Oh, okay. So yours is
Okay,
a
it's
little
negative
off.
2.5 and negative 1.
Okay, negative 2.5 and negative what?
Negative 1.
I don't have negative 1. What did you get?
I plugged in wrong.
Okay, we have everybody
Sorry.
plugging things in wrong. Let's try it again.
Okay.
Maybe calculators wasn't the way to go. Negative 3x squared over 2, and then plus
Okay,
4x.
now I have negative, sorry, negative 17.5 and 2. I put the square down.
So negative 17.5, the minus is from the part of the problem itself, and then 2 right here, right? So this ends up being negative 19.5, right? Everybody good with that? I want to show you a way that you can verify this with your calculator. Are you ready? I know you just used numbers in your calculator, but I want you to verify the actual work we did. The part that I circled in red or boxed in red, I mean, that's actually your mathematical work, right? And if you made an error in that step, obviously it would affect the answer at the end. Agreed? So what we'd like to be able to do is we'd like to be able to have the calculator verify for us from the original problem that my answer of negative 19.5 at the end is right. Does that sound like a good step? Okay. So erase what you have in y1, and I want you to put the original equation in y1 instead. Negative 3x plus 4. It's just a line. There's nothing exciting about it, but just put it in for fun. Okay. So it's a decreasing line. It crosses the x-axis at 4. And I want you to go ahead and look at the graph for it. So why don't you start your graph at 0 and go out to, say, I don't know. You just go from 0 to 10. Since our graph's supposed to go from 2 to 5 for sure, just look at 0 to 10. And then if you want to hit zoom 0, that's zoom fit, it will automatically pick a good y-axis window, although probably about negative 10 to 10 would be appropriate if you didn't have one already in there. Does everybody see the graph? Decreasing line from left to right, all look good. Okay, go back out into your regular screen. I'm going to show you 2 ways to do this problem, all right? The first way is to hit the button that says Math. Does everybody have the Math button? And then the number 9. There's 2 different things that could happen when you did that. And it's depending on how your calculator is set up and how old your calculator is. It either says FNINT. Whose calculator says that? Okay, we've got 3. Most of you do. Okay, so Brooks and Shannon, yours don't say that? They don't say FNINT. Do they have the script S notation? Yes. Do you know how to do what I'm asking you to do then? No. Okay. Watch with Austin then, because that way you can see what his looks like. Okay. Shannon, you probably know what to do then, because it's pretty obvious where you put the numbers in and everything else. Okay. Everyone else has an older version of this same process of what Shannon's doing, which is just fine. What you're going to do first is you're going to put in y1. So how do you get to y1? You hit vars. Vars is over there by your keypad and by the delete button. Does everybody see vars? Hit y vars. It's a y variable. Var stands for variable. It's a function, so select function, and then select y1. So once you go through all of that, we should be back to your regular screen in your calculator, and it should now look like this. There's no comma yet, but you're going to put a comma next. So does everybody have that so far? Can everybody see find the comma key? Okay. The next thing you put is you put a comma and then you put x. I'll tell you what this means in a second. Then you're going to put another comma. I'm sorry, I already said that comma. You're going to put the lower limit, which is 2, and then the upper limit, which is 5. This is telling your calculator, I want the integral of the function that's in y1, where the variable is x, from the x value of 2 to the x value of 5. That's what you're telling your calculator. It's just the language that it uses. Okay, and then if you hit enter, it should tell you negative 19.5. Did it? Yikes, that's good. It worked. All right, look good? All right, and of course, if it told you something that you didn't get as your answer, then you made a mistake in your work, right? Now I want to show you another cool feature. Go back to your graph. Hit graph. Everybody can see the graph the way we discussed, right? Okay, I want you to hit second. I think it's trace. Make sure. Yeah, second trace. The second trace is the calc menu. Calc as in calculate, not calculus, but it does have some calculus features in there. Second calc. So second trace is calc. And then there is an option in there that looks like this one. It looks like the script S. Do you see it? I don't remember which number it is. What number is it on the screen? 7. Do you see number 7? Looks like that script S. Select it. When you select that, it goes back into your regular screen, and what does it ask you for? Lower bound? Lower limit. What's our lower limit? 2. It's the lower number of this. 2. It's the number on the bottom of my integral up here. So hit 2, right, type the number 2 and hit enter. And then it should say upper limit or upper bound, something like that. So the upper number of this is 5. So hit the number 5, hit enter, and what happened? It actually shaded it in, which is kind of cool, so you can see it, and it also gave you the answer along the bottom of the screen. You see that? This is a really nice one because you can see the picture happening, but it's also handy because if you take a look at it, or it's a little picky, let me say it that way. Because if you take a look at it, the only way this will actually work is if your screen actually shows the proper x values in it. That's why I was so careful in making sure your screen actually showed from 2 to 5. So like let's say that you had done this and you were supposed to be doing the integral from 12 to 15, but your screen was in the standard negative 10 to 10 window, then your calculator will give you an error when you try to do this. So you actually have, if you want to do it within the graphing screen, you actually have to be able to see the x values that you're trying to interpret it at. Does that make sense? So in terms of just processing it quickly, the quickest way to do it is to do Math 9. But I wanted you to see that that's actually a really useful tool that allows you to have the answer to any problem, or at least an approximation for it if we end up with something like a square root involved or something like that. Okay. Any questions on that process? Okay, kind of cool, right? Okay, let's take a look then. All right, let's take a look then at the second example. All right, so now we're working with something that's got some trig involved. I know you guys love trig. So we're going to do a little trig on this particular problem. We're finding an antiderivative. So what's the antiderivative of 1 plus sine of x? All right, first the 1. What's the antiderivative of the 1? X. And then the antiderivative of sine is cosine. And is it positive or negative cosine? It's negative. Because remember, the derivative of cosine is sine. So this one's backwards. This is what's getting everybody on their basic skills quizzes too, by the way, is negatives. We've got negatives all over the place that keep causing problems for people. And then we don't need the plus c, right? No, not necessary. I'm going to do that evaluation bar here at the back. The top number is pi, and the lower number is 0. When you're dealing with trig functions, almost without fail, they're giving you values that you can use unit circle for. So it's a good idea to think about it from a unit circle perspective, because a lot of your unit circle values do give you square roots in them, which means if you plug them into your calculator, they're not going to give you an exact expression anyway. Now this one's not really all that messy, but there's a couple in your homework that are a little bit less friendly if you're not thinking about unit circles. We're going to plug in that number pi. So I need pi minus the cosine of pi. And all that's supposed to be minus 0 minus the cosine of 0. So pi is pi. That's fine. We've got a roughly 3.14 value there. What is the cosine of pi? It's negative 1. So I actually have the opposite of negative 1 here. So I have minus negative 1. So there's going to be a plus 1 there in a minute. I've got a minus here. Of course, the 0 is 0. What is the cosine of 0? That's positive 1. So if we're careful on our signs, these two negatives become a positive, right? And this negative become a positive, which means my answer is actually pi plus 2. Am I in your way, Hannah? Okay, let me move. Back here. Now, if you evaluate this in your calculator, of course, it's not going to spit out back at you pi plus 2, but it will spit out back at you something that is an approximation for that, right? So you could actually verify this is going to be approximately 5.14, right? 3.14 plus 2, about 5.14. And then if you actually let your calculator do what we did with either the function integration or Math 9, feature that kind of thing, then it's actually going to give you an approximation that's going to be the same approximation. Okay. All right, let's try another one. All right, so the next thing that we're going to do is we're going to use the second part of the fundamental theorem. Now, let me pause for a moment to let you know the first part of the theorem and the second part of the theorem are saying the same thing. They just look a little different. And I'm going to ask you for one of them or the other of them, potentially both, but probably one or the other on your exam. So this is the part where you get to memorize something that you know is going to be on the exam. Okay, so it's going to be either the part 1 or the part 2. All right, so the part 2 says the following. It says if we have a function that's continuous on the interval a, b, and we've got this capital F of x, which is the antiderivative of the lowercase f of t from a to x, then the derivative on the left, the derivative of what's on the left-hand side is the equivalent to what's on the right-hand side, but what's different on the right-hand side here as opposed to down here? What do you see? And there's no script S, right? What else?
The upper bound doesn't have a value. There's an x that's going to be.
Yeah, there's something about that that's a little interesting, right? This has an x up here. And what does it look like they've done? Because this one says f of t. What's it look like they've done? Yeah, that's what it looks like, right? It looks like over here that this x is in the same place the t was before. So it really just looks like all they did on the right-hand side was eliminate all the calculus symbols and take that upper bound x and put it in for where the t was. That's what it looks like. Okay? So in some sense, that is what's going on here, because what you're doing is you're taking the derivative of an antiderivative. It's like saying, let's multiply by 5 and then divide by 5, and what do we get? Well, whatever we started with, right? It didn't change. It's kind of like that. Now, there is something else that's going on here. So this is where I was wanting to do. I started at the beginning and I didn't mean to. This is where I wanted to do an example of something very simple. So let's say that we had a number, or I had an integral, and it went from 2 to, say, x, like they're giving me, of 3t plus 1 dt. Okay, very simple. What this theorem is actually saying is that if this is capital F of x, and we take the derivative of it, so capital F prime of x, that the derivative is really just 3x plus 1. That is all you have to do if you're asked to find the derivative in this form. Now look at that, and then look at the next example and tell me what is different about your actual next example from this particular problem that I just made up. Yeah, it's not just x, is it? There's a sine x on the top. That's somehow different. I mean, there's more going on in sine x than there is just if the function up there was x. So the question then becomes, how does that change things? Well, the first part of it is the same. So let's take a look at that. If I'm finding the derivative, the first part is the same. I take that sine x and I replace it, replace the t with the sine x, just like that. What was t plus 2 is now sine x plus 2. That's exactly what that last page told me I do. Take what was up top and plug it in. Here's what's missing from that previous slide because it didn't apply. This is actually a chain rule. Because I don't just have x on the top, I have sine of x. So I need to then multiply by the derivative of sine x. What's the derivative of sine x? Derivative, not antiderivative. What's the derivative? Cosine x. This is something akin to when we were working with problems that looked like this. What did we do? Well, we brought the 5 down, we rewrote the sign, and we decreased the power. But once we were done with that overall process, we had to then take the derivative of what was inside. Okay? This is the corollary to that. It's the equivalent kind of statement to that. Now we're going to take it one step further. What's different about this problem than the ones we already did?
X is in the lower bound.
And there's an x in the upper bound, right? We have an x in the lower and the upper bound. That's somehow different. And it is, because if you take a look back at this theorem flat out has a number down on the bottom. This theorem only works if there's a number on the bottom. I can't have a variable in both places and apply this theorem. So what do? Well, we're actually going to use a feature that we have not used yet, but we saw it a couple of sections ago. There was one section where we said that if we had a number A and a number B, and there was a number C in between them, and we had some sort of a curve up here, we could find the area under this curve, if we wanted to for some strange reason, by breaking it into two pieces and finding the area of each piece. Do you guys remember that theorem? It said we have the ability to break the interval into two pieces. That's what we're going to use here. So let me show you how that works. We're going to take this integral, and we're going to go from x to 0. And there's nothing special about 0. You can put any number there you'd like, but 0 is just fine. Of the t squared plus 4 dt. Plus the integral from 0 to 3 minus x of t squared plus 4 dt. Because all we're really doing is we're saying that this is x, this is 3 minus x, and somewhere in between the number 0 is where we're going to break this into two pieces. So one interval goes from x to 0, the second interval goes from 0 to 3 minus x. Does everybody understand the breaking apart piece first? Okay. After I break it apart, there's still a problem, however. This piece right here looks an awful lot like the last function I did, because it had sine x up on top. This isn't just x. It's kind of like having that sine x up on the top bound. But this piece here, the first piece, it doesn't look quite like that. What's different about it? It's inverted, right? It's sort of upside down. I'd really like to have that x as the upper limit instead of the lower limit. Now, I have not actually shown you this theorem, and I did not go back, and I should have, to see where it is in your book. It has to be there, and I must have overlooked it. But there is a property in your book that tells you that if you're going from a to b from a function, this is equivalent to going from b to a if you make it negative. So inverted is a good way to describe it. If you invert the limits, if you switch them around, then you'll get the same value if you make one of them or the other, one side or the other side negative. They're negatives of each other. It's the exact same value but opposite sign. So the reason that that's helpful on this one, is because I can take this then and I can write a negative out in front. It will go from 0 to x of t squared plus 4 dt. And then I've got one going from 0 to 3 minus x of t squared plus 4 dt. It's a lot of work in the setup. So you first have to split it into two intervals, and then you have to flip that or invert the limits of integration on the first one. But now it's actually in the form that we want. And in fact, it's so nice that this particular first one is exactly in the form I want. I've got an X on top. I don't even have to do anything weird with, a product rule or something like that, chain rule or anything like that. I don't have a chain rule in this one. So this one follows exactly from the fundamental theorem of calculus, which says that I can plug the X in place of the T. And lo and behold, I have X squared plus 4. And I've still got that negative that was out in front of the limit of the integration symbol. That's still got to be there. Is everybody good then with that piece? Second piece is going to feel like the sine x example. We're going to take this 3 minus x first of all, and we're going to replace it for the t. So we're going to have 3 minus x squared, and then plus 4. But it's a chain rule, which means now I need to multiply that by the derivative of the upper value, the 3 minus x. What's the derivative of 3 minus x? Negative 1. Now this problem should feel, a little awkward. I'm asking you to do derivatives in the middle of a problem about antiderivatives, right? You're going to have that happen occasionally on these, where you have that process where you're doing two things at once. In fact, in section 4.6 on Monday, we're going to have it happen on every single problem. And I'll show you why when we get there. But we're going to be doing derivatives in the middle of antiderivatives all that section. So this is just kind of a foretaste of what is to come. What's remaining on this problem then is to simplify. So we're going to multiply this out, simplify what we've got. I've got negative x squared minus 4. The piece here that's in parentheses has to be squared, like foiled out. So this is actually 9 minus the 6x, then plus the x squared, plus the 4 that was there, and then it's times negative 1, so we have to distribute that negative. You can either combine like terms inside that second parenthesis and then distribute the negative, or distribute the negative first. It doesn't matter. I'm going to just distribute the negative and then combine everything at the end. So I've got negative x squared minus 4, minus 9, plus 6x, minus x squared, minus 4. All right, combining like terms, what do I have? Negative 2x squared. What's next? Plus 6x. And then what? Right, minus 17. Good. Your calculator can't help you with this. No Math 9 features or anything fun like that. Okay. Any question on that one? All right, next question, not a very difficult one, but I want to show you that you can actually start with some things that you were looking and working with in section 4.4 and use them in this section as well. This description does not write it for you in terms of the symbols. They actually give you a verbal description or a word description to start with. They want you to find the given area, and then they tell you about the area. The area is the region bounded by the equations y equal x squared, x equal 2, and the x-axis. So the first thing you've got to be able to do is to draw a picture of what's going on. So this is my xy axis. You know what the graph of y equal x squared looks like. Something like that, right? X equals 2 is over here somewhere. Just so that I don't have a confusion between my axes and those, I'll draw it in a different color. So it's not perfectly straight up and down, but imagine that's x equal to 2. That first one we drew was y equal to x squared. And then the x-axis, let me just draw it in, and I'll use the pink as well since I've already got it pulled up. If it were drawn well, as I'm sure it's drawn well on your papers and not on mine, but if it were drawn well, you should be able to see trapped area. Do you see trapped area on the problem? Yeah? Do you? Nobody's even nodding at me. Oh, thank you, there's some nodding. I like that. It's almost too tiny for me to shade it in, but it's right there, right? What is that trapped area? Well, that trapped area is understood to be an integral. From what to what? What are my limits of integration? 0 to 2, right? I'm starting at the y-axis at x equals 0, and I'm going out to the line x equal to 2. That's the x values of my limits of integration. And the curve that bounds it, that comes down and then goes back up, this curve that's bounding it is the equation that I want to put in here. It's the equation x squared.